Buckle up, space enthusiasts, because we're about to embark on an electrifying journey through the captivating world of space weather forecasting. Brace yourself for cosmic storms, solar flares, and celestial dances that ignite the heavens. Get ready to witness the unseen forces that shape our space environment, challenging satellites, astronauts, and even our very own technological infrastructure. The space weather. Space weather is a branch of space physics and aeronomy, or heliophysics, concerned with the time-varying conditions within the solar system, including the solar wind, emphasizing the space surrounding the Earth, including conditions in the magnetosphere, ionosphere, thermosphere, and exosphere. Space weather is distinct from, but conceptually related to, the terrestrial weather of the atmosphere of Earth, troposphere and stratosphere. The term space weather was first used in the 1950s and came into common usage in the 1990s. Later, it was generalized to a space climate research discipline, which focuses on general behaviors of longer and larger scale variabilities and effects. History. For many centuries, the effects of space weather were noticed, but not understood. Displays of auroral light have long been observed at high latitudes. Genesis. In 1724, George Graham reported that the needle of a magnetic compass was regularly deflected from magnetic north over each day. This effect was eventually attributed to overhead electric currents flowing in the ionosphere and magnetosphere by Balfour Stewart in 1882, and confirmed by Arthur Schuster in 1889 from analysis of magnetic observatory data. In 1852, astronomer and British Major General Edward Sabine showed that the probability of the occurrence of magnetic storms on Earth was correlated with the number of sunspots, demonstrating a novel solar-terrestrial interaction. In 1859, a great magnetic storm caused brilliant auroral displays and disrupted global telegraph operations. Richard Christopher Carrington correctly connected the storm with a solar flare that he had observed the day before in the vicinity of a large sunspot group, demonstrating that specific solar events could affect the Earth. Christian Birkeland explained the physics of aurorae by creating artificial ones in his laboratory and predicted the solar wind. The introduction of radio revealed that periods of extreme static or noise occurred. Severe radar jamming during a large solar event in 1942 led to the discovery of solar radio bursts, radio waves that cover a broad frequency range created by a solar flare, another aspect of space weather. The 20th century. In the 20th century, the interest in space weather expanded as military and commercial systems came to depend on systems affected by space weather. Communications satellites are a vital part of global commerce. Weather satellite systems provide information about terrestrial weather. The signals from satellites of a global positioning system, GPS, are used in a wide variety of applications. Space weather phenomena can interfere with or damage these satellites or interfere with the radio signals with which they operate. Space weather phenomena can cause damaging surges in long-distance transmission lines and expose passengers and crew of aircraft travel to radiation, especially on polar routes. U.S. National Space Weather Program. The purpose of the U.S. National Space Weather Program is to focus research on the needs of the affected commercial and military communities, to connect the research and user communities, to create coordination between operational data centers, and to better define user community needs. NOAA operates the National Weather Service's Space Weather Prediction Center. Phenomena. Within the solar system, space weather is influenced by the solar wind and the interplanetary magnetic field carried by the solar wind plasma. A variety of physical phenomena is associated with space weather, including geomagnetic storms and substorms, energization of the Van Allen radiation belts, ionospheric disturbances and scintillation of satellite-to-ground radio signals and long-range radar signals, aurorae, and geomagnetically induced currents at Earth's surface. Coronal mass ejections are also important drivers of space weather, as they can compress the magnetosphere and trigger geomagnetic storms. Solar energetic particles, SEP, accelerated by coronal mass ejections or solar flares, can trigger solar particle events, a critical driver of human impact space weather, as they can damage electronics on board spacecraft, egg galaxy 15 failure, and threaten the lives of astronauts, as well as increase radiation hazards to high-altitude, high-latitude aviation. Effects. Spacecraft electronics. Some spacecraft failures can be directly attributed to space weather. Many more are thought to have a space weather component. For example, 46 of the 70 failures reported in 2003 occurred during the October 2003 geomagnetic storm. The two most common adverse space weather effects on spacecraft are radiation damage and spacecraft charging. Spacecraft orbit changes. The orbits of spacecraft in low Earth orbit, LEO, decay to lower and lower altitudes due to the resistance from the friction between the spacecraft's surface, A, drag, and the outer layer of the Earth's atmosphere, or the thermosphere and exosphere. Eventually, an LEO spacecraft falls out of orbit and towards the Earth's surface. Many spacecraft launched in the past few decades can fire a small rocket to manage their orbits. The rocket can increase altitude to extend its lifetime, direct the re-entry towards a particular marine site, or route the satellite to avoid collision with other spacecraft. Such maneuvers require precise information about the orbit. A geomagnetic storm can cause an orbit change over a few days that otherwise would occur over a year or more. The geomagnetic storm adds heat to the thermosphere, causing the thermosphere to expand and rise, increasing the drag on spacecraft. The 2009 satellite collision between the Iridium 33 and Cosmos 2251 demonstrated the importance of having precise knowledge of all objects in orbit. Iridium 33 could maneuver out of the path of Cosmos 2251 and could have evaded the crash if a credible collision prediction had been available. Humans in space. The exposure of a human body to ionizing radiation has the same harmful effects whether the source of the radiation is a medical X-ray machine, a nuclear power plant, or radiation in space. The degree of the harmful effect depends on the length of exposure and the radiation's energy density. The ever-present radiation belts extend down to the altitude of crewed spacecraft such as the International Space Station, ISS, and the Space Shuttle, but the amount of exposure is within the acceptable lifetime exposure limit under normal conditions. During a major space weather event that includes a SEP burst, the flux can increase by orders of magnitude. Areas within ISS provide shielding that can keep the total dose within safe limits. For the Space Shuttle, such an event would have required immediate mission termination. As we conclude our journey through the captivating world of space weather forecasting, we are reminded of the profound impact that the sun's unpredictable moods can have on our technological civilization. From the awe-inspiring dance of the northern lights to the mesmerizing coronal mass ejections, space weather reminds us of the dynamic forces that shape our cosmic environment. If you found our video informative, kindly subscribe to our channel or you will miss out on our videos.